Brandon Strickland. Underground homemaker. My phone number is 630-326-3570. Thank you and have a blessed day.
All right, well, today we are going to do Chapter 9. This is the ideal gas laws. In this chapter, we will review the kinetic molecular theory again. We will do the pressure-volume relationship. We'll see that's called Boyle's law. Temperature volume is Charles's law. Mole volume is Avogadro's law. And put them all together, we get the ideal gas laws. Finally, we'll do some problems. I want to remind you when we finish this chapter, next weekend is Amnesty Weekend, okay? Friday, Saturday, and Sunday. Tutorials number 1 and quiz number 1 will all come back online, 6 o'clock on Friday. And they will go away midnight on Sunday. If you need to earn some extra points, well, this will ruin your weekend, but probably get you some extra points, I hope. Any questions?
Wait, keep it. I'll just keep it up to minutes. This is for next week. Is this for next week or this week?
This upcoming weekend.
Oh, okay. Thank you.
All right. We have talked about the kinetic molecular theory before. Basically, it's founded in the assumption that every substance in the universe has an inherent attraction to every other substance. This is due to what are known as intermolecular forces. Imagine magnetism being the force. This lump of little buckyball magnets represents a solid. Kinetic molecular theory tells us that we're dealing with solids, liquids, or gases, depending upon temperature. For a solid, the individual particles don't have enough inherent energy to break free of each other. And so they just kind of sit in the corner like a child in timeout and shake. If you put a little more energy into it, we wind up with a situation where we have a liquid. In a liquid, the particles still can't escape, but they can slip and slide all over each other. Finally, today we're talking about gases. In the gas phase, we have particles moving very quickly. They are hitting the walls of the container and each other. We'll see that the force with which they hit gives us what's known as gas pressure. A gas has indefinite shape, takes on the shape of its container. If you noted, there was lots of room in between the particles. Gases can be compressed, therefore, and they can also expand to fill the void, and they diffuse rapidly and uniformly throughout the container. Now, I said that when particles hit the wall, that basically they create what's known as gas pressure. This is the result of a calculation again. There are 500 little gas particles in here. The walls are fixed, but this guy is a floating barrier. Every time a particle runs into it, it pushes it up a little bit, and then falls, and then pushes up, and stuff like that. Now this is for 500 particles. If you have lots and lots of particles in there, you can get lots of pressure, and this thing will be nice and stable. Air pressure, atmospheric pressure is referred to. The result of all the air molecules in the mixture running into everything, including us. They exert a very significant pressure, roughly 15 pounds for every square inch. So square inch like that, right? 15 pounds of pressure. If we didn't have air inside of us pushing out, we would be smashed to bits. Just to demonstrate, this is one of the burners that you use, like on Thanksgiving if you want to fry a turkey and burn your garage down all at the same time. What we're going to do is take this guy, light it. We will take a 55-gallon drum, put a little bit of water on it, put it on this thing, let the water heat up so the air inside is now nice and hot. Seal it up and watch what happens. So let's start. We light the little guy. Here's our drum. See the steam coming out? Seal it up. This is a little swimming pool with some ice in it. Put it there for a minute, 30 seconds or so, and there it goes. We'll do it again in slow motion. Yep. Atmospheric pressure totally took this drum and just smashed the heck out of it. Isn't that neat? Atmospheric pressure is measured using barometers. Now these are a collection of old-fashioned barometers. This one is so old we even have it on the wall in the lab. This is a recording weather barometer. A little ink pen goes up and down and stuff like that. This is a laboratory device called a manometer. You have mercury in here, and you try to eyeball it so that the two things are very close together, and the difference in height gives you a pressure, whatever. These are all antiques by now. If you want to measure vacuum accurately, you use one of these digital scales that mount onto your vacuum line, and again, lots of significant figures and very, very accurate. But my favorite among the bunch is this guy. This is a little globe. It's sealed, got a blue liquid in it, and this end is open to the atmosphere. You'll note that low pressure is associated with rain. So if the pressure outside is lower than that in this, the little level of the tube comes up. Well, I grew up in Florida, and we actually had one of these sitting on our shelf because this was the 1950s, and there were no such things as satellites looking out over the Atlantic to find hurricanes. Hurricane is one heck of a storm with a very low pressure. So if you just happen to be sitting in your living room and notice that suddenly this thing started squirting out the top, you knew it was time to board up the windows and hunker down, because it was coming. Those were the days. Any questions? In lab, we will measure using a mercury barometer. Now again, this is something that's a bit of an antique. It used to be something that every student did during general chemistry. Make your own barometer. It's roughly 3 feet tall. What you do is you take this tube, open at one end, and you fill it with mercury. Then you put your thumb over the end, stick it down in this bucket of mercury, and let go. Mercury's heavy, it falls, makes a vacuum at the top, and it settles on a height. At sea level, 25 degrees centigrade, or 0 degrees centigrade, sorry, this height is 760 millimeters. This is defined as atmospheric pressure. Pressure in the atmosphere, again, air pressure pushing down. This goes up and down depending upon the level of air pressure and whatever. The height here, again, is measured in millimeters of mercury. The units that we use for gas pressure, if we are at 760 millimeters height, that is also called 1 atmosphere. That's the pressure at sea level, again, 760 millimeters of mercury. Some books will call this torr, T-O-R-R, instead of millimeters. I do millimeters, torr is kind of stupid. This is what we talked about earlier, our 15 pounds per square inch, but we will never use this measurement in class. So, we're either going to use atmospheres or millimeters. When you have a pressure that is 1 atmosphere, as far as significant figures go, this is an exact number. Likewise, 760. They're both considered definitions. The relationship between the two is this factor of 760. So, if you are given atmospheres and you want to convert it to millimeters, multiply by 760. The opposite, to convert millimeters to atmospheres, simply divide. So the two are readily changeable. Any questions on the definitions here? All right, let's do our first relationship here. That is pressure volume. We'll see that this is referred to as Boyle's law. Boyle's law tells us that the volume occupied by a fixed quantity of gas is inversely proportional to the applied pressure. It's an inverse relationship. Now, in order to demonstrate this, we can use this guy. This is a piston in a sealed container here with a gas and a pressure gauge. All right? If we take our piston and we put a very small mass on it, that'll work. Well, gee, I didn't see the needle move at all. So, very small pressure and very large volume. Okay? But if we increase the pressure by doing something like dropping an anvil on it, we have a small volume now and a high pressure. That's the inverse relationship. Small pressure, large volume, large pressure, small volume. Now, anvils are fun to play with, but let's go ahead and do this and keep track as we slowly adjust our volume here. We're going to plot pressure and volume on this little curve. We start off with a big volume and a very small pressure. As the pressure starts to increase, the volume decreases. You will note, however, that this is a nonlinear relationship. Has to be nonlinear if you think about it. Because down here, as your volume approaches zero, the pressure would approach forever because you actually can't get to zero because the gas itself has an inherent volume. This particular curve is what's known as a hyperbola. It's a hyperbolic dependence. And the real issue with this curve is that it's nonlinear. People don't like things that are nonlinear. It's very difficult to do predictions. Well, mathematicians tell us that if we have a hyperbola, we can linearize that by doing what's called a reciprocal plot. So if we plot volume here versus 1 over pressure, we get this. Nice straight line. That's much more comfortable. Easy to predict based on the straight line. Now, mathematically, what this means is that volume is directly proportional to 1 over pressure. Volume, this is the proportionality sign. Directly proportional to 1 over pressure. Whenever you have a proportionality sign like this, mathematically, you can replace that little alpha-like symbol with an equal sign and a constant. Volume is equal to some constant times 1 over P. Proportionality can always be replaced by equal K. K is actually the slope of this line. All right, so let's think about our situation here. We said that volume was equal to some constant times 1 over P, right? If we take this and multiply both sides by P, we get this equation. PV equals K. Now with our piston, we had two situations, two extremes. One with a very light pressure, one with a very significant pressure. Large volume, small volume. If this is our initial state, PV is going to be equal to K. Our equation says so. So let's write that down. And because we're calling it initial, we'll do P1, V1. Over here, PV is still going to be equal to a constant. We'll call this our final state, P2, V2. Now, this is exactly the same piston. It's the same gas. That means that the constants are exactly the same. It's a closed system. If the two constants are exactly the same, that means that PV1 must equal PV2. This is what we refer to as Boyle's law. PV1 equals PV2. This is Robert Boyle, Englishman. I don't think I like him. Funny hair, really funny shirt. Doesn't look like he's much fun at all. But okay, that's Robert Boyle. Any questions? Well, then let's see how we do this in a problem. Here we have 12.5 liters of gas. Our pressure is 0.82 atmospheres. We're going to change our pressure to 1.32, and we want to know our final volume. So think about our piston. We start off here, we go here. What's the volume? All right, classic Boyle's Law problem. PV1 equals PV2. We're looking for the final volume, that's V2. So we'll solve the relationship for V2 and then substitute. There's Boyle's Law. We're after V2 once again. And that's P1 V1 over P2. Up top, P1 is 0.82. V1, 12.5. And P2, 1.32. When you work these problems, the only thing you really need to think about and check is to make sure that the units are the same. Atmosphere, atmosphere, or millimeter, millimeter. Likewise, liters or milliliters, as long as they're the same, that's fine. So, take this and substitute in. This is P1, this is V1, this is P2. Atmospheres will cancel. 0.82 times 12 divided by 1.32. We're at 7.8 liters. Our first Boyle's Law problem. Isn't that something? Any questions? Well, let's do another. Here we have a pressure in millimeters, a volume in milliliters. Once again, just make sure that they're all the same. Milliliters, milliliters, our pressure, our final pressure will be in millimeters of mercury. So, again, it's a Boyle's Law, P1, V1, P2, V2. We're looking for the final pressure, that's P2. We will take this expression, solve for P2. Boyle's Law. P2 is going to be P1 V1 over V2. Simply substitute. P1, 35 millimeters. V1, 150 mils. V2, 50 mils. So we're starting at 150 and we're decreasing the volume to 50. Once again, we will cancel milliliters. And our math, quite simply, is 35 times 150 divided by 50, 106 millimeters. Now, what if I was being ugly and said, okay, I want this answer in atmospheres? What would you do? You would remember the relationship. 1 atmosphere, 760 millimeters. We have millimeters, we need to divide by 760, 0.14 atmospheres. Remember the 760 to 1 ratio. Very useful. All right, in this chapter, we will have 3 tutorials. First one, Boyle's Law.
Yes.
Here we'll have a problem. Typically, you're going to have to do 1 or more metric conversions. Here we have an initial pressure of 5 atmospheres. We want the resultant pressure in atmospheres, so that's good. We have a volume in milliliters and a volume in liters. The way I do these, the way I think is the easiest to do these, is just to make a list of what you've got and do whatever conversions you have to. So here's our list. P1, the initial pressure, 5 atmospheres, no problem. V1, 50-50 mils, again, no problem. We're looking for the final pressure, that's P2, in atmospheres, so that's good. And finally, our V2 was given in liters, multiplied by 1,000 to get milliliters, so they match. You could also convert this to liters, it doesn't matter. It's going to cancel, remember? So let's take our Boyle's law, P1, V1, P2, V2, rearrange it, and solve for P2. P1, V1 over V2. We will cancel milliliters down here. 5 times 550 divided by 620. We get this number, 3 significant figures, 4.54. Any questions? Let's do one more. Go ahead and take the data here and set up your data table. We're looking for the resultant volume, that's V2. We want it in liters. V1 is in milliliters, so we need a conversion. This is in millimeters, and this is in atmospheres. So set it up and do your conversions. All right, we know P1 in millimeters. P2 is given in atmospheres. Remember, 1 atmosphere is 760 millimeters. So I'm going to multiply this by 760 to get P2 in terms of millimeters. We're looking for V2. Boyle's law tells us V2 is P1 V1 over P2. We substitute. Millimeters will cancel, and we're left with 3.58 liters. Any questions? Boyle's law is simple. Math is simple. The concept is simple. Yeah.
For like for 18 MV, multiplied by 760 to get
Right. Multiply by 760 to go from atmospheres to milliliters. Divide to go the other way. All right. That's the end of Boyle's law. Let's move on to Charles's law. Charles is the guy's last name, by the way. And this is the temperature-volume relationship. Now, what we're going to do here is take this poor innocent balloon, and we are going to dump liquid nitrogen on it. Liquid nitrogen is minus 196 centigrade, so it's really, really cold, okay? So, let's go ahead and do this and watch what happens to our poor balloon. The balloon sees the guy coming, gets nervous. There it goes, trying to get away, can't. And by George, once you get it all soaked up with liquid nitrogen, the balloon is just a figment of what it used to be. But as the liquid nitrogen is evaporating, the balloon is warming back up. And as it does, the volume increases. Back to where we were. So, what did we see? As the temperature decreased, the volume decreased. As the temperature increased, the volume increased. That's a direct relationship. Temperature goes down, volume goes down. Temperature up, volume up. So, before we look at the actual mathematics of it, let's do something a little more scientific than simply mess with a balloon. Okay? Balloons are fun, nitrogen is fun, but if we were to do this in the lab, we would take samples of gases. We would change their temperature and measure the volume. Now, in terms of how much gas, let's measure this in terms of moles. We have 1 mole of gas, half a mole of gas, whatever. Let's start off here with 0.25 moles of gas. We take this container, we change the temperature, and measure the volume. Yep, this is just what we expect, isn't it? Temperature goes down, volume goes down. Never trust one determination. Do it again, half a mole. Temperature goes down, volume goes down. Let's do it one more time just to be sure. 0.75 moles. Yep, nice linear relationship for all three of them. Okay, nice quantitative answer, right? But look at these curves, these lines. They're all heading down, aren't they? They're heading, it looks like, to the same spot. In fact, if you take and extrapolate each of these down, you'll see that all of these lines intersect at exactly the same spot. Now, at this particular temperature, the prediction is the volume should be 0. And we know that that can never happen. You can never get there because it's going to have some volume of its own. This intersection is minus 273 centigrade. This phenomenon represents another temperature scale where this is going to be 0. It's going to be, in fact, called absolute 0. This is 0 on what's called the Kelvin scale. And of course it goes up, just like the centigrade scale did. We start at minus 273 centigrade, that's 0 Kelvin. Kelvin is 0 here. This is centigrade is minus 273. The two are going to always be 273 degrees apart. And Kelvin's going to be more. All right. Let's go back to Charles's law then. Our little lines tell us that volume is directly proportional to temperature. We know that we can take the proportionality and change it to an equal sign and a K. V is equal to KT. Let's isolate K like we did last time. K is going to be V over T. Now, in our experiment with our balloon, we had two states. When it was very cold, the balloon had a small volume. we'll call that the initial state, and that's our constant. When we allowed it to warm back up, this is our final state, and this is the same constant. Therefore, V1 over T1 must equal V2 over T2. This is the expression for Charles's law. It's a direct relationship. Temperature goes up, volume goes up. Temperature goes down, volume goes down. We saw Boyle, it didn't look very fun. This is Charles. He looks like, well, nice guy. Kind of ruddy. He's a Frenchman. No stupid wig. First time I saw this picture, this is a very young crowd. Does anybody know who Barry Manilow is? Yeah, well, that's him. Actually, I think Barry Manilow and Charles could be the same person. Nonetheless, Charles was a very interesting guy. In fact, he was the very first person to take a ride in a gas-filled balloon. There he goes. He had his little balloon and his gondola and just took a nice trip over the French countryside. Now, here he is filling his balloon. They took sulfuric acid and iron. This is a single replacement reaction, isn't it? With hydrogen acting as a metal. So, we get hydrogen gas being formed. This reaction gets really hot. It's taking place in the barrel there, and they're filling the balloon with it. As the very hot hydrogen comes up into the balloon space, it cools, right? What happens to the balloon? It gets small. So it gets big and small depending upon the temperature. That's how Charles figured out his law, by watching his little balloon. So they took this thing after it was all full and hooked his gondola up to it. He took 2 or 3 bottles of wine with him and went for a trip across the countryside. Roughly 1,800 feet, and just flying gently over the south of France. Well, okay, that sounds neat, doesn't it? But this was 1783, long time ago. So he's floating, decides it's time to come down. Looks, and here's this little village, little peasant village down there. He said, that's neat, I'll land here. So we started letting out hydrogen gas. Balloon started to drop. We're landing over there at the village. Now, mind you, peasants in 1783 in France were not very literate. And suddenly they saw this thing in the sky with this guy in it coming down in their village. So they reacted, as you might expect French peasants to do. They attacked it with pitchforks, knives, and dogs. Fortunately, Charles lived through it. He never did it again, though, but he lived through it. This was a hydrogen balloon. It's a good thing that they didn't do the other thing that French peasants often do, and that is use torches and throw them at it, because we know hydrogen is very explosive, right? Nonetheless, hydrogen is the perfect gas for a balloon. It's cheap. We have tons and tons and limitless quantities of it. It just has the one problem that it burns. Well, it is so good. We use helium today, but we're out of helium. That's bad. but you can't use hydrogen. The reason is everybody was using hydrogen, and they made massive airships. This is the Hindenburg. It's a German craft. 1937. It would carry 30, 40 people in its belly, and it was designed to fly from Berlin all the way across the Atlantic to New Jersey. All right, first flight. Okay, here we go. They all had a party in the belly, and they're flying. They made it fine all the way across the Atlantic. They're coming in for a landing. Turns out that there's a thunderstorm in the area. Now, the skin on this is a very thin metal. What they think happened was the thunderstorm put a static charge on the skin of the dirigible. As it came in for a landing, they started, just like Charles, started venting their hydrogen so that they would come back down. As they did it, the hydrogen suddenly exploded, and that was the end of hydrogen-filled balloons. Nobody does a hydrogen balloon since this. It's just way too dangerous, but hydrogen is still the best gas for it. Any questions? Well, let's go back to the Kelvin scale. Kelvin scale is important because anytime you do a temperature volume gas law problem, you must use Kelvin. Okay, just have to remember, has to be Kelvin. We all know that water freezes at 0 and boils at 100, right? On the Kelvin scale, water freezes at 273 and boils at 373. Quite conveniently, there's 100 little degrees in between here and here. So they match, but they always differ by a factor of 273 degrees. Remember, Kelvin is always going to be bigger than centigrade because we had 273 to whatever centigrade is. So, let's just do a couple quick conversions. Remember, our conversion factor is 273. All you do is take centigrade, add 273 to it, we get Kelvin. You notice the little degree sign disappears. I don't know why they did that, but it's just Kelvin. Minus 150, 123 Kelvin. And we just saw 100 centigrade, 373 Kelvin. So rule 1 to remember, it must always be converted to Kelvin. Let's do a problem. We have 50 ml sample. We're at 26 degrees centigrade. We heat it until the volume is 62. What's the final temperature? Okay, simple Charles's law problem. We know V1, 50 mils. We know T1, 26.4 centigrade. And we know V2, 62 mils. Again, make sure they're all the same units. The one unit that we can't deal with, of course, is the centigrade here. We must change that into Kelvin. So let's see, we're looking for the final temperature, that's T2. T2 is going to be V2, T1 over V1. V2 is this, T1 is this plus 273, or about 300 Kelvin. And finally, V1, 50 mils. Plug it all in. Our milliliters will cancel. 62 times 300 divided by 50. Again, way too many significant figures. We have 3, so let's round this to 374. Now, if the problem asked you, what's the final temperature in centigrade? What would you do? Remember, they differ by 273. Kelvin is always bigger. So just take this, subtract 273, we get 101. Any questions? Well, obviously, our second tutorial, if the first one was boil, it's only fair that we have one for Charles. We have a gas system, initial volume and temperature of 11,000 mils. And again, this is in centigrade. We're changing our volume to 7.66 liters, and we're looking for the final temperature in Kelvin. So, just like with boil, the way I do it is I look at these and I just fill out my little table. V1, 11,000 mils. T1, 106 centigrade. We add 273 to it. V2, we're in liters, it has to be the same. We could change this to liters or change this one to mils. I just did mils, multiplied by 1,000. And we're looking for T2. We start off with Charles's law. V1 over T1, V2 over T2. Solve for T2, V2, T1, V1. We substitute. Milliliters will cancel. We're left with Kelvin. And we're at 264 Kelvin. What would this be in centigrade? You would take 264, subtract 273. Any questions? On Blackboard, both Boyle and Charles look just like this. Well, there's one more gas law we have to cover. Remember we did this experiment here, right? Doing an experiment like this is lots of work. It really is in the lab. When you do something and you get a set of data, you always want to try to get as much information out of it as you can. So there's one more relationship we could look at. And that is if we hold the temperature constant and simply change the number of moles, what happens to the volume? So we'll deal only with this set of points. Now, intuitively, totally intuitively, as we increase the moles, we're just adding more gas, aren't we? If we add more gas, we expect the volume to go up. It should be a direct relationship. This is called the mole-volume relationship. So we'll take data like this at constant temperature and we'll plot it. And sure enough, it's a straight line. It's a direct relationship. This is called Avogadro's law. It goes to Avogadro. Number of moles and the volume. Simple, direct relationship. Okay, so we have three gas laws. We have Boyle, Charles, and Avogadro. Boyle told us volume was proportional to 1 over P. Charles said volume was proportional to T. And Avogadro said volume was proportional to N, the number of moles. Well, if volume is proportional to all three of these guys, you can simply take and multiply them all together, and it's still going to be proportional. So we can write it this way. Volume is going to be proportional to NT over P. Okay. Now, what do we do every time we have a proportionality sign? We change it, don't we? To an equal sign and a constant. So we can do it again. But you know what? We've used K a lot. I'm tired of using K. It's my equation, my constant. I can call it anything I want. So I am going to call it R. Uppercase R I'll use. And I'm going to call R the universal gas constant. Volume is going to equal R times the number of moles times the temperature divided by the pressure. Well, okay, that's an equation, but it's not a fun equation. If we take both sides and multiply by P, this side will give us PV. This side will give us N, R, and T. This is a much more fun equation. PV equals nRT. It even rhymes with itself. This is the ideal gas law. PV equals nRT. With this equation, if you know anything, you could calculate everything else. Kind of neat. The only problem is, what the heck is R? We can't do anything if we don't know what R is. But we do know what R is. Avogadro told us. Remember, 1 mole of any gas at 273 Kelvin, 1 atmosphere, has a volume of 22.4 liters. 1 mole, 22.4 liters. Okay, so let's take this and solve for R. PV over NT. Here's our pressure, 1 atmosphere. Our volume, 22.4 liters. Number of moles, 1. Temperature, 273 Kelvin. Plug it all in. Now at this point, usually I would click my little button and things would cancel, right? Little red X's would appear everywhere. They don't. They don't. If we take this and multiply it all out, we get the ungodly answer of 0.082 with units of liter atmosphere per mole per Kelvin. I can't remember this either. So if you ever need it on a quiz or exam, it'll be there. When you use this, things to remember. You must use atmospheres, you must use liters, and of course Kelvin. So let's see how we do a PV equals nRT problem. We're looking for moles of argon. It doesn't matter if it's argon, does it? All gases are the same. But we're looking for how many moles of it. We have 18.6 liters. We're at 293 Kelvin. And the pressure is 2.35 atmospheres. This is PV equals nRT problem. And we're solving for N. N is going to be PV over RT. We put in our pressure, 2.35 atmospheres. Our volume, 18.6 liters. R, 0.082 liter atmosphere per mole per Kelvin. And finally, temperature, 293 Kelvin. Okay. Atmospheres, top and bottom will cancel. Liters, top and bottom will cancel. We have Kelvin and per Kelvin. They cancel. Per mole in the denominator comes up top. Calculate it all out. 1.81 moles. PV equals nRT. So the last tutorial in this chapter is the PV equals nRT tutorial, the ideal gas law. We have a gas system, volume, moles, and temperature. 5 liters, 0.396 moles, 291 Kelvin. What's the pressure in atmospheres? We can do this. Simply, there's our list. We're looking for the pressure. We know the volume, the number of moles, and the temperature. Pressure is going to be nRT over V. Substitute, multiply it out, 1.86 atmospheres. If we were asked to give this in millimeters, what would we do? We would multiply by 760. 1408 millimeters. So let's go ahead and set up one more. Make your table. We have 1.56 atmospheres. This is in milliliters. Remember, it has to be liters. Here's our number of moles. We're looking for temperature in Kelvin. Okay, here's my list. Volume in mils must go to liters. Remember, we need atmospheres, liters, and moles, and Kelvin. Here's our pressure, volume, number of moles, looking for temperature. Take PV equals nRT, solve for T. PV over nR. P, V, N, and R. 1.56 times 8.4 divided by 0.082 divided again by 0.7. We're at 225 Kelvin. If we wanted centigrade, we would subtract 273. All right, let's look at 4 old exam questions. Once again, this is one that I put on the exam thinking that everybody would get it right. Almost nobody got it right. G. I try, I do. What does Boyle law require? P1, V1, P2, V2. That sounds really familiar, doesn't it? That's Boyle's law. Okay, that's good. PV equals a constant. Well, that's where this guy came from, wasn't it? PV1 and PV2, same constant. So yeah, that's right. How about this silly thing? If you take this, multiply both sides by V1, and then both sides by P2, what do you get? V1, V1, P2, V2. Yeah, that's the same as this. They're all the same, and they're all correct. Well, I was so disappointed that everybody missed this one, so the next exam, I did it again with Charles's law. So which of these are Charles's law? That's a good guess. Charles's law. You look at your 3x5 card. V1 over T1, V2 over T2. That's what we're looking for, right? V1, T1, V2, T2. That sounds really familiar, but that's Boyle's law, isn't it? Not Charles's. Charles's V over T. So that's wrong. TV was a constant. No, V over T was a constant. Well, here we have something, but again, multiply both sides by V1, and then by T2, you get this. And we've already said that's wrong. So this is none of the above. All right, a real calculation. We have 450 milliliters of the gas, 1 atmosphere. We reduce the volume until the pressure is 5 atmospheres. Our final volume is what? Well, this is going to be a standard Boyle's law problem. P1, V1, P2, V2. We're looking for the final volume, that's V2. So we will do P1, V1 over P2. Substitute, 450 mils, 1 atmosphere, 5 atmospheres. Atmospheres will cancel, giving us just mils for volume. 450 times 1 divided by 5 is what? 90. And our last one for today. When you are comparing centigrade and Kelvin, what's true? 1 Kelvin is a larger temperature change than centigrade. Nope. Remember, they're exactly the same. Centigrade and Kelvin are never numerically equal. How could they be equal if Kelvin is always 273 higher? They can never be the same. Only readings in centigrade can be converted to Fahrenheit. That's stupid. So B is our correct answer. All right. What do we know about gases? They consist of molecules in constant and random motion. Yes, they do. Pressure arises from collisions with the wall. Yes, it does. Why do we call these ideal gas laws? Because we're assuming that there are no attractive or repulsive forces. Ideally, there would not be. In reality, tiny, tiny bit. When they hit each other, they stick for like a billionth of a microsecond and then go away. At very high pressures, this makes a difference. Otherwise, it doesn't. The volume is negligible. Yes, it is. The gas laws are entirely intuitive. Let's prove that with 3 little short video clips.
If the number of gas molecules in a container is doubled, with no change in the temperature or volume, the number of collisions between gas molecules and the container walls doubles, which translates into a doubling of pressure.
Number doubles, pressure doubles. Makes sense.
If the temperature of a constant volume of gas is increased, the molecules of the gas move faster, and each collision exerts a greater force on the walls of the container. In addition, because the molecules move faster, the number of collisions between gas molecules and the container walls increases, and therefore, so does gas pressure.
You heat it up, they go faster, they hit harder, temperature goes up, pressure goes up. Finally, volume.
If the volume of a container of gas is reduced by half, but the amount of gas remains fixed, more collisions will occur between gas molecules and the container walls in a given time, leading to an increase in the force exerted on those walls.
If the volume goes down, the number of collisions goes up, and so does the pressure. Totally intuitive. All right, here's our list of tutorials. Today we added 3. We are doing chapter 11 next week. There is 1 tutorial with chapter 11. Once we do that one, we're done. Get busy if you haven't started. Remember, if you need, Amnesty Weekend is coming up. Friday, Saturday, Sunday, Friday at 6. Off Sunday at midnight, tutorials, and the quiz. Good luck, guys. Thank you, and I will see you Wednesday for hydration of aloe.